you should be able to begin.
Okay. Thank you for the opportunity to present here today. I'm actually very happy to be following Scott Bailey because Scott and I started out working together at the Naval Research Lab 35 years ago. And I'm not sure if either one of us would have expected to be making this kind of presentation, but I appreciate the chance that we have to make it. My name is DeLand. Most of my time is spent leading the processing team for the OMS profiler data, and I'll talk more about that instrument in a minute. Matt Kovalevsky is the systems engineer for this project who has experience with previous airborne and space projects at Goddard. Pete Colarco is an atmospheric modeler who focuses on aerosols and also integrates aerosol models with global climate models. Luis Ramos Izquierdo created the optical design for MASTAR and has refined it through a couple of generations that I'll show you. And Billy Nemekos has been leading the fabrication and integration of this instrument. Next slide, please. So Scott's talk gave you a little bit of introduction to why we're doing this instrument. Stratospheric aerosols are not the heavy aerosols we're used to speaking of in the troposphere. There's a relatively thin layer. But there are multiple components. There's a naturally occurring background, which is also referred to as the umbel layer. But there's also transport into the stratosphere from the troposphere due to anthropogenic sources, as well as impulsive injections from volcanic eruptions and major forest fires called pyrocumulonimbus events. An important aspect of those injections is that while they occur at a specific place and time, once they get into the stratosphere, you have a memory because the plume can travel around the globe, sometimes multiple times, and last for months. And so we really need to understand where the contributions go from these plumes. Scott also mentioned the fact that these aerosols can cool the atmosphere and offset some of the warming that you would expect to get from greenhouse gases. So to fully monitor these aerosols, we need satellite measurements. We want good temporal sampling because of the variability. We also want spatial sampling because the plumes can be injected in a relatively small place. And we'd like to have vertical resolution because their transport in the atmosphere depends greatly on what altitude they're at. And so we feel like limb scattering observations, where you're looking horizontally at the atmosphere and viewing the scattered light, is the best way to satisfy those requirements. As currently an operational instrument, I'll simply focus on the OMS limb profiler, relying on Sony NPP, to make these measurements, but we think we have some options to improve the data that's being collected by OMS. Next slide, please. So our design is called the Multi-Angle Stratospheric Aerosol Radiometer, or MASTAR. The diagram you see on the right is an example of what we would eventually fly in a satellite. I'll show you where we are at this point. Designed to be a CubeSat-sized instrument, we created the original design with 3D CubeSat form factor. We used the OMS limb measurement technique where you're looking at the atmosphere scattered off the limb. Then we've done a few things to enhance and also simplify on that. Instead of viewing in one direction, we actually have 8 different viewing directions of the atmosphere. This helps deal with a sensitivity issue that OMS limb has because the aerosols are very they respond very strongly to the different scattering angles that you're viewing at, and so you have the difference in sensitivity between northern and southern hemispheres. The extra viewing apertures also give us more spatial sampling, including between orbits, and give us a way to help understand the phase function and the size distribution of the aerosols themselves. Next slide, please. This is just a simple table showing some of the parameters that we've designed the instrument for. We put a vertical slit on the atmosphere to view roughly between 10 and 60 kilometers. In 6 of the 8 apertures, we actually had 2 wavelengths in this design. We started out with 670 nanometers from our original design for heritage with OMS limb, and then we've added a second slit using 850 nanometers to get better coverage lower in the atmosphere. We also have 2 apertures that view at 350 nanometers in order to help altitude registration, because pointing for a limb instrument is very critical. You need on the order of 1 arcminute and preferably better accuracy. And so the initial design, spacecraft instruments were not capable of supporting that, and so we needed an onboard technique to continue that. Next slide, please. So this is a little diagram of the evolution of how we arrived to where we're at. We started out with internal funding from Goddard in 2016 and built a very simple design called GAMS at that point that had 6 apertures, different type of central mirror, and I'll talk about that mirror in just a moment. Just use a single wavelength per aperture angle, and that was simply operated in the lab. We then got IEP ICD funding in 2017 for an 18-month project. Upgraded the design to 8 apertures and added the second science wavelength, as I described. At the end of that project, ESTO asked us what we could do to improve TRO, and we said, well, flying it would be helpful. And they said, well, what would it take to do that? And so with their generosity, we worked towards the IEP extension that you see in the next panel. If you click one more time, it should pop up. Yeah, and so this talk is focused on going from the crawling to the walking stage, as we consider it. And the last column shows you some of the ideas that we would try to go for in a flight instrument. Next slide, please. So what have we done at this point with our original design? One of the things we've done is to simplify the optical path. The figure in the top right shows you the optical design that we built in the laboratory in 2018, where we have 8 apertures. The light from all 8 apertures goes into a central octagonal prism. That prism directs the light down towards the CCD. But in order to get it focused on the CCD, we had to design some optics after the prism to focus the light. What we figured out for the flight version of this was that we could remove those aft optics and put the slit very close to the detector. That simplifies the optics and actually makes it more robust because we've removed a fair number of lenses that, as we saw in our initial design, were on the order of 2 millimeters in diameter, so we don't have to go through as much effort placing those. We've also modified the split apertures because we realized that the dynamic range in the atmosphere is very bright down low, fainter up high. And so by tapering the slit, we can reduce some of the dynamic range that we have to deal with. And the bottom right panel shows a close-up of that current optical design. Okay, so this is what we've been working towards to set up the instrument to fly on a high-altitude balloon. Since the original lab version was only designed to operate at room temperature and pressure, we needed to configure an enclosure to hold the instrument, and that's the small can that you see shown schematically on the bottom left. It's still only about 15 inches tall, so it's not very big. You can see some of the basic components on the right-hand side that show how we would go from the optics up in the top, where the light comes in and is focused down onto the CCD, to include some of the other components required for flight. Next slide, please. So we've been working towards that. We've been setting up to have software that would let us operate in both the typical data-taking mode, where we collect an overall sample about every 40 seconds from averaging some number of measurements that then can be determined in process. The picture on the right shows you sample measurements from taking the instrument up on the roof at NASA Goddard and collecting data during clear sky. And one thing you can notice is that the splits only use a very small amount of the CCD. And so we could certainly save on data storage by simply integrating the portions that we need instead of worrying about pulling down the whole CCD. Next slide, please. And so then reality check it for us. We have been working towards a balloon flight in fall of 2020. NASA Goddard shut down facilities on March 18th, which put a screeching halt to most of our procurement, fabrication, and assembly, and able to do some software development, but not fully testing things. Given the uncertainty of when we might be able to get in and try to finish it, and the desire to deliver a quality instrument, we pulled out of the balloon flight schedule for this fall. We do plan to complete assembly, do some environmental testing, year and hopefully try to get a flight in 2021.